Uncovering distant worlds, discovering exoplanets and their significance for life. For generations, humans have gazed at the night sky, wondering whether life might exist beyond our home planet. The notion that distant planets, possibly resembling Earth, could harbor living organisms has inspired imaginative tales and sparked deep philosophical reflection. However, until recently, such musings remained within the realm of conjecture. That changed when scientific advancements began delivering tangible answers, ultimately confirming the presence of planets beyond our solar neighborhood. These planets, known as exoplanets, world-circling stars outside our solar system, have reshaped our understanding of the cosmos. Not only have we proven that other planets exist across the universe, but we've also unlocked new possibilities concerning the existence of life far from Earth. But how were these remote celestial bodies discovered, and what might they mean for the search for extraterrestrial life? The journey toward discovering exoplanets is a fairly modern one. The very first confirmed identification of an exoplanet took place in 1992. But reaching this point was the result of decades of scientific evolution, beginning with hypothetical models and continuing with the aid of rapidly improving technologies. During the 1980s, astronomers started devising strategies to identify planets orbiting distant stars. Yet, this was no easy task. Stars shine so intensely and are so far away that any accompanying planets are generally lost in their brilliance. A significant breakthrough occurred when astronomer Alexander Volshin, alongside his associate Dale Frail, made a historic discovery, not around a typical star, but orbiting a pulsar, which is a dense, highly magnetic, and fast-rotating neutron star. The pulsar, known as PSRB 1257+12, emitted steady pulses of radio signals. The consistency of these pulses enabled Volshin and Frail to detect faint gravitational disturbances caused by nearby orbiting planets. Although these initial planets were small, rocky, and inhospitable to life as we know it, their detection marked a crucial milestone. For the first time, planets outside our solar system had been confirmed to exist. The field experienced a dramatic shift with the 2009 launch of NASA's Kepler Space Telescope. Designed with a clear purpose to locate Earth-sized planets residing in the so-called habitable zone around stars, Kepler aimed to identify planets where liquid water and possibly life could exist. Kepler relied on a method called the transit method. In essence, this technique involves observing slight reductions in a star's brightness that occur when a planet passes in front of it, as seen from Earth. These temporary dips in light, though minimal, provide valuable clues about the planet's size, orbital period, and even atmospheric properties. Because Kepler continuously monitored a fixed portion of the sky for more than 9 years, it managed to track thousands of stars and detect minute dimming effects caused by planetary transits. In 2012, Kepler's findings shocked the scientific world. It had detected over 2,300 candidate exoplanets. Many were similar in size to Earth or even smaller, and several were located within their stars' habitable zones. This was a transformative moment. We had moved beyond merely discovering exoplanets to identifying worlds with potential conditions for life, scenarios once limited to fiction. Among Kepler's discoveries was Kepler 22b, a planet located within the habitable zone of its star, roughly 600 light-years from Earth. Though far away, the implications were immense. Habitable planets might be more common in our galaxy than previously believed. As observational techniques improved, the scope of discoveries widened dramatically. By 2015, scientists had cataloged over 1,000 confirmed exoplanets, and new discoveries were coming at a growing pace. Many of these defied earlier models. For instance, some planets were significantly larger than Jupiter and orbited very close to their stars, while others fell into a category called super-Earths, planets larger than Earth but smaller than Neptune or Uranus. In addition to the transit method, astronomers developed various other ways to uncover exoplanets. One such technique is the radial velocity method, also known as the Doppler method. It involves observing the tiny wobbles a star makes due to the gravitational influence of an orbiting planet. These wobbles shift the light from the star toward the red or blue end of the spectrum depending on whether the star is moving away from or toward Earth. By tracking these spectral shifts, astronomers can detect planets without ever directly seeing them. Another technique is direct imaging, which attempts to visually capture exoplanets by blocking the overwhelming light of the host star. Though technically challenging, especially given the contrast in brightness, this method has been successful in identifying young, hot planets that emit infrared radiation. What makes the field of exoplanet science so fascinating is our ability to now study alien worlds with remarkable precision. Scientists utilize a process called spectroscopy to analyze the atmospheres of these far-off planets. By studying the way light interacts with atmospheric particles, either passing through or reflecting off them, researchers can identify key molecules such as water vapor, oxygen, or methane, all of which could hint at biological processes. This process, known as atmospheric characterization, is helping us to explore the chemical makeup of these worlds, potentially enabling us to recognize signs of life from afar. It's a window into alien environments that, not long ago, we could only imagine. The pursuit of Earth analogs, or Earth 2.0, remains among the most thrilling quests in science today. Though we haven't yet found a perfect match, the discovery of thousands of exoplanets, some within their stars' habitable zones, offers a glimpse of hope. In the near future, with the deployment of advanced tools such as the James Webb Space Telescope and the Nancy Grace Roman Space Telescope, scientists expect to gain unparalleled insights into exoplanet atmospheres and compositions. So what does this all mean for humanity? The detection of exoplanets has altered how we perceive the cosmos. It suggests that Earth is not an isolated island in a lifeless void but part of an immense, dynamic universe filled with potential. Whether we eventually find life beyond our planet or not, the search itself teaches us valuable lessons about Earth, the environmental factors necessary for life, and our position within the greater cosmic framework. By reaching out to explore these remote planets, we are doing more than looking for life. We're confronting the deepest questions of our existence. What makes a planet suitable for life? How does biology emerge and thrive under different conditions? And ultimately, what role do we play in this vast and mysterious universe? The revelation of exoplanets reminds us of something humbling and beautiful. We are threads in a much larger cosmic tapestry, one that's just beginning to unfold. Unifying the universe. A complete rephrasing of the theory of everything. Each individual fragment symbolizes a distinct element of our cosmos, the natural forces, the actions of matter, and the architecture of space and time. Now, picture all these fragments locking seamlessly into place, unveiling one all-encompassing image that clarifies everything from the tiniest subatomic particle to the vastest galaxies. This unified vision is the holy grail of physics, a comprehensive theory of everything a singular, cohesive structure that integrates all natural forces into one clear and rational framework. At the dawn of the 20th century, the field of physics was split into two foundational branches. The first was classical mechanics, which accurately described the motion of everyday objects. The second was electromagnetism, the science explaining electric and magnetic interactions, brilliantly articulated by James Clerk Maxwell in the 1800s. Maxwell's equations illuminated the fact that light itself is an electromagnetic wave, uniting electricity and magnetism into an elegant theoretical structure. However, a scientific revolution unfolded with the rise of quantum mechanics and general relativity, two distinct theories that revolutionized our grasp of reality in very different ways. Quantum mechanics, pioneered in the early 20th century by scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, unveiled that at microscopic scales, particles do not behave like tiny solid objects. Instead, they resemble waves described by probabilities and uncertainties. This wave-particle duality, alongside Heisenberg's uncertainty principle, dismantled traditional Newtonian assumptions. Meanwhile, Albert Einstein's theory of general relativity, developed in 1915, redefined gravity. Einstein argued that gravity is not a force in the classical sense, but a consequence of space-time being curved by mass and energy. This interpretation significantly deviated from Newton's viewpoint and provided a far more accurate model of the universe, particularly under extreme conditions like black holes and cosmic expansion. Though immensely effective within their own domains, quantum mechanics and general relativity fundamentally clashed. Quantum mechanics excelled at explaining atoms and subatomic particles, while general relativity thrived in describing celestial and cosmic phenomena. Yet, merging these frameworks into one cohesive theory remained problematic. A pivotal step toward a unified theory came during the mid-1900s with the creation of quantum field theory (QFT). QFT fused quantum mechanics with special relativity, laying the groundwork for understanding particle behavior and fundamental interactions. Progress further accelerated with the realization that three of the four fundamental forces, electromagnetic, weak nuclear, and strong nuclear forces, could be incorporated into a single model. This model, called the Standard Model of Particle Physics, represents the culmination of decades of effort. It categorizes elementary particles and explains their interactions through force-carrying particles. A major milestone came in the 1970s when the electromagnetic and weak nuclear forces were unified into what's known as the electroweak theory. Physicists Sheldon Glashow, Abdus Salam, and Steven Weinberg were awarded the Nobel Prize in 1979 for this achievement. The model was further validated in the 1980s with the confirmation of the Higgs boson, which explains how particles attain mass. Yet, despite its impressive scope, the Standard Model does not account for gravity. Gravity continues to be described by general relativity, and integrating it into the quantum realm has proven deeply challenging. This is where the pursuit of a theory of everything intensifies. By the 1980s, physicists began to entertain the idea that the universe's essence lies in minuscule vibrating strings. String theory proposes that these strings, not point-like particles, are the fundamental units of reality. Their different vibrational modes correspond to the various particles and forces we observe. Crucially, string theory includes gravity by predicting a particle known as the graviton, a quantum mediator of gravitational interaction. This makes string theory a potential bridge between quantum mechanics and general relativity. However, it comes with a caveat. String theory requires extra spatial dimensions beyond the familiar 3. It posits up to 10 or 11 dimensions, which are presumed to be compactified at scales too small to detect with present-day instruments. Despite its aesthetic beauty and mathematical sophistication, string theory has not yet provided experimentally verifiable predictions, and its abstract nature makes it difficult to test. Critics argue it lacks empirical grounding, while proponents maintain hope that it will ultimately unlock the universe's secrets. Yet string theory is not the sole contender. An alternative, known as loop quantum gravity (LQG), seeks to marry quantum mechanics with general relativity without invoking strings. Instead, LQG suggests that spacetime is itself composed of discrete, quantized loops at the smallest scales. Though less mature than string theory, LQG aligns more directly with Einstein's equations and does not require extra dimensions or highly abstract constructs. So where do we stand in the quest for a theory of everything? Despite significant strides, complete unification remains out of reach. The ultimate integration of the four primary forces, gravity, electromagnetism, strong nuclear, and weak nuclear, continues to elude scientists. New insights from quantum mechanics, string theory, and quantum gravity emerge regularly, but challenges persist. A primary obstacle is the vast difference in scale between quantum mechanics and general relativity. Bridging this divide demands innovative mathematical frameworks and entirely new ways of perceiving space, time, and matter. The journey toward a theory of everything is defined as much by the profound questions it raises as by the answers it uncovers. Whether string theory, loop quantum gravity, or another yet unknown model holds the key, the ongoing search reflects humanity's relentless curiosity and desire to understand our place in the cosmos. In the end, this theory is not only about deciphering the workings of the universe, but also about grasping the essence of our existence. And that pursuit will continue to inspire thinkers and dreamers for generations to come. Infinite realms. A journey through the multiverse concept. Picture an endless archive filled with every conceivable book, each one representing a unique universe. Every volume contains its own distinct history, laws, and events. Some of these worlds bear a close resemblance to ours, differing only in subtle ways, while others are dramatically dissimilar, functioning under entirely alien principles of physics. This immense archive of books symbolizes the multiverse, an ever-growing expanse of parallel realities existing side by side with our own. The multiverse concept stands as one of the most perplexing and debated ideas in current physics. It proposes that the cosmos we occupy is merely one among countless potential realities. But where did this notion originate? Let's explore its beginnings and how it has developed through time. Hints of the multiverse idea date back to the early 1900s, during a transformative era in physics. The rise of quantum mechanics and the expansion of cosmological theories introduced revolutionary ways to perceive reality. Within quantum mechanics, particles didn't behave in predictable ways. Their actions were governed by probabilities. This led to the Copenhagen interpretation, which proposed that particles exist in multiple potential states simultaneously until measured. Yet, the true catalyst for the multiverse theory came from a different development, the many worlds interpretation of quantum mechanics, introduced by physicist Hugh Everett in 1957. Everett's radical proposal stated that instead of collapsing into a single definite outcome upon observation, every possible result of a quantum event actually takes place, each in its own distinct universe. Imagine flipping a coin. In one universe, it lands heads. In another, tails. Both outcomes happen, but in separate parallel realms. Everett's theory was groundbreaking. It suggested our reality is just one of infinite parallel worlds, each born from different quantum possibilities. Although initially viewed as more of a mathematical curiosity than a provable theory, it planted the seeds for the multiverse model. Later developments in cosmology, particularly in the late 20th century, pushed the multiverse concept toward mainstream scientific thought. The introduction of the inflationary model of the cosmos by Alan Guth in the early 1980s laid essential groundwork. In essence, cosmic inflation proposes that immediately following the Big Bang, the universe underwent an incredibly rapid expansion. This rapid stretching of spacetime allowed minor quantum disturbances to grow into the massive galaxies and structures we observe today. More intriguingly, inflation theory hinted at something even more extraordinary. Space could expand at different rates in various regions, giving rise to separate zones of spacetime, each evolving into its own universe with unique physical laws. This concept led to the theory of eternal inflation, the idea that this expansion continues endlessly, generating an infinite number of pocket universes or bubbles, each distinct from the others. This framework, known as the bubble multiverse, reimagines the Big Bang not as a singular event, but as part of an ongoing process of universe creation. Each bubble forms its own universe, complete with its own physical parameters, gravity, the speed of light, even the basic rules of physics themselves. As this vision of the multiverse gained support among cosmologists, it also found resonance in string theory, a mathematical framework aimed at unifying all forces of nature. String theory posits that the fundamental components of reality aren't point particles, but tiny vibrating strings. These strings exist in more than the familiar three spatial dimensions and one time dimension. They operate in multiple extra dimensions. String theory introduces the idea of a landscape of possible solutions, where each configuration corresponds to a different set of physical constants. In this context, the multiverse naturally emerges. Each unique compactification of the extra dimensions could produce a separate universe with its own laws. The vast number of ways these dimensions can be folded leads to a staggering number of potential universes. Proponents of string theory argue that the multiverse is not only plausible, but perhaps inevitable. The continuous formation of universes, each with its own properties, could explain why the constants of our universe are so precisely tuned for life. If there are enough universes, statistically, some will have just the right ingredients for life to arise, purely by chance. If true, the multiverse theory holds profound implications for how we understand reality. Consider a few major consequences. Explaining fine-tuning. One enduring question in cosmology is why physical constants, like gravity's strength or the electron's mass, are so perfectly balanced for life. The multiverse suggests that among infinite universes, some will naturally have the right conditions, removing the need for special explanation. Redefining probability. If every potential quantum outcome happens somewhere, the traditional understanding of probability is challenged. The notion that everything that can happen does happen could transform how we view chance and determinism. Limits of empirical evidence. One of the biggest obstacles to the multiverse theory is its lack of direct testability. In most versions, other universes are entirely isolated from ours, making them impossible to detect. This raises a critical issue. Is the multiverse a scientific hypothesis or merely philosophical speculation? Despite its speculative nature, the multiverse idea continues to energize scientific inquiry in cosmology, quantum physics, and string theory. Should we ever develop the means to test it, we could enter a new phase of understanding, one in which our universe is just one chapter in a much grander cosmic story. Whether or not the multiverse truly exists, the theory urges us to grapple with the most profound questions about the nature of existence and reality. For now, it remains a captivating possibility, an invitation to rethink our place in a potentially infinite cosmos. Breakthroughs in the pursuit of fusion energy. Exploring nuclear fusion involves examining the fundamental process responsible for fueling stars, including our own sun. It stands as the most energy-efficient mechanism recognized by scientists, capable of generating vast quantities of power by merging lightweight atomic nuclei, like hydrogen, into heavier ones, such as helium. For many decades, researchers have attempted to mimic this phenomenon on Earth in hopes of tapping into an essentially unlimited, clean energy source. But what progress have we made so far? To fully appreciate the monumental advancements in fusion science, we must revisit the field's origin and examine the critical discoveries that have shaped its development. The narrative of nuclear fusion begins in the 1930s, when physicists such as Hans Bethe first deciphered the mechanisms behind stellar fusion. Bethe's research uncovered that stars, including the Sun, produce energy by combining hydrogen atoms into helium through multiple nuclear reactions. This process, known as the proton-proton chain reaction, emits an immense quantity of heat and light, sustaining a star's temperature and radiance. His pioneering work laid the foundation for all future fusion-related efforts on Earth. Yet it wasn't until the 1950s that scientists began serious attempts to replicate this energy generation process on Earth. Around this time, the idea of nuclear fusion reactors, devices designed to initiate and control atomic fusion and capture the energy, started to take form. The initial significant step in this direction came with the invention of magnetic confinement fusion. This technique relies on extremely strong magnetic fields to hold superheated plasma, a charged, high-energy gas, in place within a controlled chamber long enough to enable fusion reactions. This concept led to the creation of the tokamak, a torus-shaped donut-like device built to maintain plasma at astonishing temperatures, millions of degrees Celsius, without letting it touch the chamber walls. In the early 1960s, Soviet scientists, including Andrei Sakharov and Lev Artsimovich, made key strides by building the first tokamak reactors, capable of reaching the extreme temperatures needed for fusion. Despite their promise, these early machines couldn't maintain stability or create more energy than they used. Fusion, at least on Earth, remained out of reach. The main difficulty was that the plasma inside a fusion chamber had to be heated far beyond the melting point of any known substance, around 100 million degrees Celsius, and had to remain contained long enough for fusion to happen. No existing material could survive such conditions. Despite these enormous technical barriers, the ambition for fusion power endured. In fact, the last few decades have seen remarkable progress, driven by new technologies and collaborative international efforts. One of the most pivotal developments came with the launch of the International Thermonuclear Experimental Reactor ITER, a landmark project designed to construct the most sophisticated and largest fusion reactor on the planet. Located in southern France, ITER is a joint venture among 35 countries, including the European Union, the United States, China, and Russia. The mission of ITER is to show that fusion can serve as a viable, long-term power source by achieving a net positive energy output, where more energy is generated by the fusion reaction than is required to sustain it. Although ITER remains under construction and is not expected to be fully operational until the late 2020s, other fusion facilities have achieved important breakthroughs. That same year, a major accomplishment came from a much smaller American research center, the National Ignition Facility (NIF). NIF uses a different technique known as laser-driven fusion or inertial confinement fusion. Here, extremely powerful lasers target a minuscule hydrogen pellet, compressing it to the extreme temperatures and pressures similar to those at the heart of stars. In 2021, NIF announced a global record in fusion energy output, producing close to 1.9 megajoules of energy in a single reaction. This marked a major leap toward the goal of ignition, the point where fusion produces more energy than it consumes. This achievement was crucial because it demonstrated that fusion could be initiated and controlled under laboratory conditions. It also broadened our understanding of fusion's potential and what might be technologically achievable in the near future. Yet, significant hurdles remain before fusion can become a dependable energy source. The next milestone for NIF and similar projects is to scale up their technologies and boost efficiency, ensuring that the fusion reactions last longer and produce greater energy yields. Nevertheless, major challenges persist. The engineering scale needed to create and sustain net-positive fusion reactions is enormous. Reactors must manage the extreme temperatures and plasma stability, while materials that can withstand prolonged exposure to such harsh environments must be developed. Additionally, the costs of constructing and operating fusion reactors remain steep. Still, the rapid pace of innovation in fusion research is deeply encouraging. With growing support from governments and the private sector, the dream of capturing stellar energy on Earth feels increasingly within reach. Scientists, engineers, and innovators across the globe are laying the foundation for a future powered by the same process that fuels stars. While the race toward functional nuclear fusion continues, each advancement brings us closer to unlocking one of the universe's most powerful energy sources, one that could permanently transform how humanity energizes its world. Unveiling the Higgs boson, a landmark in particle physics, the identification of the Higgs boson marks one of the most remarkable milestones in contemporary physics. It's not just because it resolved a long-standing scientific enigma, but because it also showcased extraordinary human creativity, engineering brilliance, and theoretical vision. The tale of the Higgs boson is one of relentless dedication, stretching across nearly 50 years from its original theoretical prediction to its actual experimental detection. At its core lies a deceptively simple, yet deeply profound question: what is the source of particle mass? In the early part of the 1960s, physicists were assembling what would later be termed the Standard Model of particle physics, a comprehensive theoretical structure designed to explain the most basic constituents of matter and the forces acting upon them. This model was groundbreaking in many ways, but it had a significant flaw. It couldn't account for how particles gained mass without violating essential symmetries of the universe. These symmetries were fundamental to the correct behavior of particles and forces. According to the model's math, particles such as the W and Z bosons, which are responsible for carrying the weak nuclear force, should have no mass. Yet, observations indicated they had substantial mass. Without a coherent explanation for this mass, the whole theory remained unfinished. To visualize this, consider a bustling room filled with people. If someone tries to walk through the crowd, they're slowed down by the people around them. This resistance is similar to how particles gain mass as they pass through the Higgs field. The field interacts differently with various particles depending on their characteristics. Some become heavier, others remain unaffected. If such a field were real, it would suggest the existence of a special particle, the Higgs boson, a quantum disturbance within that field. Proving this particle's existence became one of particle physics's most pressing challenges. But detecting it required immense energy due to its predicted high mass, making it elusive for decades. This led to one of the most ambitious scientific projects ever attempted, the creation of the Large Hadron Collider LHC. Situated near Geneva, Switzerland, and operated by CERN, the European Organization for Nuclear Research, the LHC is an enormous underground particle accelerator. It was engineered to collide protons at nearly light speed, recreating conditions similar to those immediately following the Big Bang. These collisions would break particles apart and allow new, heavier particles to emerge, possibly including the Higgs boson, if it was indeed real. After extensive design and development, the LHC officially started in 2008. Thousands of engineers and scientists from across the globe joined forces to design sophisticated experiments focused on finding the Higgs boson. The most important of these were the ATLAS and CMS detectors, both constructed to record and study the brief signs of new particles created in these high-energy impacts. Identifying the Higgs boson was an incredibly demanding task. Researchers had to detect minute signals buried in a sea of other particle interactions. What made it even more challenging was that the Higgs boson decays almost instantaneously after forming, leaving behind faint clues that are hard to distinguish from background activity. The data required meticulous filtering, interpretation, and verification before any credible claim could be made. Finally, on July 4, 2012, scientists at CERN publicly shared that they had observed a new particle matching the characteristics of the Higgs boson. Both ATLAS and CMS experiments independently verified the discovery with exceptionally strong statistical certainty. This moment was celebrated as a historic advancement in physics. It filled a critical gap in the Standard Model and validated the presence of the Higgs field, the very field responsible for giving particles their mass. Moreover, the confirmation of the Higgs boson opened doors to new lines of investigation in fundamental physics. It could eventually help solve deeper puzzles like the nature of dark matter or the true behavior of gravity. One way to conceptualize the Higgs field is to imagine the universe as a giant canvas. Particles are like brushes painting on it. The texture of the canvas resists brush strokes to varying degrees depending on the brush type. Similarly, the Higgs field resists different particles in different ways, effectively giving each a unique mass. The finding of the Higgs boson stands as a towering scientific success. Yet it also signals a new beginning. Researchers are now studying the Higgs boson in greater detail, searching for anomalies or patterns that might suggest phenomena beyond the standard model, like supersymmetry or hidden dimensions. Essentially, the Higgs boson acts as a portal to deeper layers of reality. It helps us understand how mass arises, how matter binds, and what lies beneath the surface of existence itself. Revolutionizing computation. The quantum paradigm. The concept of quantum computing emerged from the realization that classical computers, powered by bits, might not efficiently solve certain problems. Bits, the basic unit of classical information, can exist in one of two states, 0 or 1. While this binary system suffices for many tasks, it's inadequate for problems requiring immense computational power, such as simulating molecular behavior at the quantum level or factoring large numbers for cryptography. In 1981, Feynman proposed a novel idea. Instead of relying on classical bits, why not exploit quantum mechanics itself? Quantum mechanics, the branch of physics dealing with particles at the smallest scales, introduces phenomena like superposition, being in multiple states at once, and entanglement, instantaneous connections between particles regardless of distance. Feynman suggested designing a machine harnessing these properties to simulate quantum systems more efficiently than classical computers. Building upon this, in 1985, physicist David Deutsch of Oxford University developed a mathematical model for a quantum computer, laying the groundwork for understanding how such a machine could function. To grasp how quantum computers operate, we delve into two fundamental quantum phenomena: superposition and entanglement. Superposition. In the quantum world, particles like electrons don't just exist in one state at a time. They can exist in multiple states simultaneously. Imagine flipping a coin. It can land heads or tails. In the quantum realm, the coin can be in a superposition of both heads and tails until observed. Quantum computers exploit this, allowing a quantum bit, or qubit, to be both 0 and 1 simultaneously, vastly increasing computational power compared to classical bits. Entanglement. When two quantum particles become entangled, their states are linked regardless of distance. Measuring one instantly reveals the state of the other, even if they're light years apart. In quantum computing, entanglement enables qubits to work together in ways classical bits cannot, allowing quantum computers to solve complex problems exponentially faster than traditional computers. With these principles established, the next step was developing algorithms harnessing qubits' power. In 1994, physicist Peter Shor introduced an algorithm capable of factoring large numbers exponentially faster than any known classical algorithm, a game changer, as factoring large numbers underpins RSA encryption, widely used for securing online communications. If a quantum computer could break RSA encryption, it would revolutionize cybersecurity. Shortly after, in 1996, Love Grover developed an algorithm enabling quantum computers to search unsorted databases faster than classical computers, a task traditionally requiring examining each entry individually. Grover's algorithm demonstrated that quantum computers could accelerate a wide range of tasks beyond number factoring, from optimization problems to machine learning. These developments sparked interest across academia and industry, initiating a race to build functional quantum computers. However, constructing a quantum computer is no simple feat. Quantum states are fragile, affected by factors like temperature, noise, and electromagnetic radiation, making it challenging to create stable qubits. Several approaches have emerged to overcome these challenges. Trapped ions. This method traps charged atoms' ions using electromagnetic fields and manipulates them with lasers. Each ion acts as a qubit, with interactions controlled by laser pulses. This approach has shown promise in lab experiments, leading to small-scale quantum computers. Superconducting circuits. utilizing superconducting materials, conductors with zero resistance at extremely low temperatures. These circuits behave like artificial atoms and serve as qubits. Companies like IBM and Google have made significant progress with superconducting qubits. Notably, Google's Sycamore processor achieved quantum supremacy in 2019 by solving a problem that would take classical supercomputers thousands of years. Topological qubits. A more speculative approach, topological qubits aim to be more error-resistant by encoding information in the quantum system's topology. While largely theoretical, this method promises to address one of quantum computing's biggest challenges: error correction. Despite the elusive nature of fully functional large-scale quantum computers, significant strides have been made in building quantum processors capable of solving specific problems. Beyond hardware breakthroughs, advances in quantum error correction, communication, and cryptography are progressing rapidly. Quantum computing's potential extends beyond speed. It could unlock solutions to complex problems across various fields. Material science, designing new drugs or better solar panels. Artificial intelligence, creating more efficient machine learning models. For instance, quantum computers could simulate chemical reactions at the atomic level, a task classical computers struggle with, leading to breakthroughs in drug development, energy storage, and new materials. Today, companies like IBM, Google, and Microsoft are at the forefront of making quantum computing a practical reality. Startups like Rigetti Computing and Ionc are also pushing boundaries. Governments worldwide are investing heavily in quantum research, recognizing its potential to reshape industries from finance to healthcare. However, quantum computing also presents new challenges. If quantum computers can break traditional encryption schemes, how can we protect our data? This is where quantum cryptography comes into play, offering new ways to secure information through quantum mechanics principles. Biolecta. Ultimately, quantum computing is still in its infancy, but its potential to change the world is vast. From solving problems too complex for even the fastest classical supercomputers to unlocking new technologies, quantum computing may be the next frontier in our understanding of the universe and how we manipulate information to change the world. Visualizing extra dimensions and brain concepts. Imagine yourself existing on a flat, two-dimensional surface like a sheet of paper. Your movement is restricted to just two directions: forward and backward, or left and right. Now, imagine being informed that there are additional directions beyond your perception, directions that extend above and below your known plane of existence. Though it may seem surreal, this is the foundational idea behind the scientific concept of extra dimensions. This idea stretches our understanding of space and fundamentally challenges the way we view reality. The belief that there might be more than the conventional three dimensions, length, width, and height, has intrigued theoretical physicists for more than 100 years. However, it was only in the latter half of the 20th century that this notion started gaining structure and scientific footing, particularly with the development of string theory and brain models. Historical foundations of higher dimensions. Though it may seem modern, the concept of additional dimensions has older roots. The earliest major effort to merge gravity with electromagnetism using extra dimensions emerged in the 1920s, pioneered by physicists Theodor Kaluza and Oskar Klein. Kaluza, a physicist from Germany, proposed that gravity could be described within a five-dimensional framework beyond the commonly accepted four dimensions of space and time. Building on Kaluza's insights, Klein suggested that this fifth dimension could be tightly compacted on an unimaginably tiny scale, which would make it unnoticeable in everyday life. This idea, which became known as the Kaluza-Klein theory, was an imaginative attempt to merge fundamental forces, yet remained speculative due to the lack of any experimental proof at the time. Nevertheless, as scientific advancements in quantum mechanics and relativity progressed, the notion of additional dimensions began to assume a central role, especially with the rise of string theory. String theory and the call for more dimensions. String theory came to prominence in the 1980s as a powerful model aiming to unify all forces in nature. According to string theory, the most basic units of reality are not point-like particles, but instead tiny vibrating strands or strings. The frequency at which each string vibrates determines the type of particle it manifests as. For this theory to function mathematically, more than just the usual 3 spatial dimensions and 1 time dimension are required. In fact, string theory implies the presence of 10 dimensions altogether, 9 spatial and 1 temporal. These extra dimensions are thought to be compactified, curled up so minutely that they evade current experimental detection. This compactification of extra dimensions became essential to the mathematical integrity of string theory, allowing it to propose a coherent structure for reality. The emergence of brane theory. As string theory matured, attention shifted toward even more exotic ideas, most notably, branes, short for membranes. Branes are multidimensional entities that can exist within these hidden dimensions. While a single point represents 0 dimensions and a string is one-dimensional, branes can have several dimensions. A 2-brane, for example, resembles a flat sheet, while a 3-brane is a 3-dimensional shape like a cube. One of the most transformative ideas in the 1990s came from what's now called M-theory, an overarching framework that includes string theory. According to M-theory, our entire universe might be a 3-brane embedded in a space of higher dimensions. In this setup, all the familiar matter and energy we experience are confined to this brane, while other branes and dimensions could coexist, invisibly layered around us. Reimagining gravity and its strength. One of the more profound consequences of brane theory is the rethinking of gravity's behavior. Unlike electromagnetic and nuclear forces, which may be trapped on our brain, gravity might be free to move into the additional dimensions. This could explain why gravity appears so weak compared to other fundamental forces, because it spreads out through extra dimensions, diluting its strength in the observable universe. Transforming our cosmic understanding. The introduction of extra dimensions and branes opens the door to several revolutionary insights. Merging all forces together. Extra dimensions might offer a pathway to unite all the natural forces into one elegant model. In the context of string theory, the presence of additional dimensions helps account for particle behaviors and force interactions, including gravity, under a single unified structure. This pushes science closer to achieving the elusive theory of everything. Unseen realms and hidden universes. If extra dimensions truly exist, they suggest there may be entire domains of reality inaccessible to our senses. According to brane theory, our universe could be a single 3-brane floating in a multi-dimensional space. There might be other branes, perhaps entire universes, existing parallel to ours, separated not by distance, but by dimensions beyond our reach. Clues to dark matter and dark energy. Some researchers speculate that these hidden dimensions might help explain 2 of physics' greatest puzzles: dark matter and dark energy. These mysterious phenomena make up most of the universe's mass and energy, yet remain undetectable by traditional means. If gravity can move into extra dimensions, it might be interacting with unknown forms of matter or energy that lie beyond our current understanding. A new view of the universe's birth. Brane theory also reshapes our ideas about how the cosmos began. One hypothesis suggests that the Big Bang might have resulted from the collision between 2 branes. If true, the visible universe may be just one consequence of a much grander and multidimensional chain of events. Current limits and future prospects. Despite the elegance of these theories, they remain unverified. We have yet to observe higher dimensional effects or detect branes directly. The idea of extra dimensions remains a captivating possibility, but still lies within the speculative realm of theoretical physics. Some physicists propose that as technology progresses, we may eventually detect evidence of these extra dimensions, perhaps through high-energy particle experiments or precise astronomical observations. Until such proof emerges, the exploration of extra dimensions and brain theory will continue to be one of the most thought-provoking frontiers in science. Ultimately, the ideas of extra dimensions and brains invite us to reimagine everything we know about existence. They push the boundaries of space, time, and reality itself. They hint at a cosmos far more intricate and mysterious than we once believed, one that challenges our perceptions and stretches the limits of what we dare to imagine. The puzzle of lost knowledge in black holes. Picture yourself standing at the edge of a colossal black hole, an enigma and one of the most formidable phenomena in the entire cosmos. As you move closer, something unusual captures your attention. Matter, light, even data regarding what enters this abyss seems to vanish, as if erased completely and irretrievably. But is it truly gone? Or does that information persist in some mysterious, unknown fashion? This conundrum is at the core of what is famously known as the black hole information paradox, one of the most profound dilemmas in theoretical physics today. To grasp this mystery, we must explore its beginnings, the breakthroughs that unveiled it, and the continuing pursuits aimed at unraveling its secrets. But Hawking's findings defied that belief. In 1974, he made an astonishing announcement: black holes release radiation. This form of radiation, now famously referred to as Hawking radiation, is produced due to quantum interactions occurring just outside the event horizon. It appears as though the black hole gradually loses energy, potentially shrinking over time and eventually disappearing entirely. This insight was revolutionary. It indicated that black holes are not eternal. They can dissipate. However, this very revelation introduced a troubling implication. What happens to the information that fell into the black hole once it evaporates? But here's the complication. Hawking radiation seems utterly devoid of any trace or imprint of the material that once fell in. It appears completely random. If the black hole fades out and the information is nowhere to be found, then it seems to have been wiped out, contradicting the fundamental principle that quantum information is never lost. Imagine sending a highly detailed manuscript, a complete record of an object, into a black hole. Once it crosses the event horizon, it disappears. We might expect that the data about the book still exists somehow, albeit in a form we can't observe. But Hawking's theory proposes that when the black hole evaporates, the data could vanish with it. It would be as if the book had never existed. Such a conclusion is deeply unsettling. If black holes have the power to erase information, then it suggests that quantum mechanics, our most successful framework for understanding microscopic phenomena, could be flawed or incomplete. This is the heart of the information paradox. The burning question of whether information that enters a black hole is lost forever, or whether there exists some cryptic mechanism through which it remains intact. This paradox has ignited a persistent debate among the brightest minds in physics for decades. While a few have suggested that information might genuinely be annihilated, implying a potential need to revise quantum theory, the majority uphold the idea that information must be retained. Prominent thinkers like Leonard Susskind and Juan Maldacena have staunchly supported the concept of information preservation. They've introduced multiple theories that might reconcile the paradox, proposing that information could be stored or released in ways we don't yet comprehend. One of the most compelling ideas comes from the holographic principle. This notion proposes that the data about everything falling into a black hole might not be lost at all, but is instead encoded on its event horizon in a flattened, two-dimensional format. In essence, just as a hologram can hold three-dimensional data on a flat surface, the event horizon could contain the entire story of all matter it has absorbed. If this is true, the radiation emitted could, in theory, carry this data, just not in any recognizable form to us. Another fascinating proposal is known as the firewall hypothesis. Proposed by researchers such as Alessandro Strominger and Samir Mathur, it challenges the classical view of the event horizon. Instead of being a quiet, featureless boundary, it could be a blazing region of extreme energy, a firewall that obliterates anything entering. This idea could offer a path to conserving information, but it also requires a radical shift in our understanding of space, time, and black hole structure. Despite years of exploration, the information paradox remains a puzzle without a definitive answer. Hawking's discovery fundamentally altered our perception of black holes, but it also created one of the most perplexing theoretical challenges in physics. Researchers continue to grapple with this paradox, proposing ever more imaginative solutions. Some suggest that resolving the issue will require a full theory of quantum gravity, a still-developing framework that could unify quantum mechanics with Einstein's general relativity. This unified theory might finally reveal what happens at the deepest levels of black hole physics. Meanwhile, scientists are designing sophisticated experiments to observe black holes more closely, especially by analyzing gravitational waves and deploying more advanced observational instruments. These might someday yield crucial clues about whether information can, in fact, escape a black hole or if it is truly doomed to oblivion. The black hole information paradox touches on the very core of reality. It questions whether the cosmos truly obeys the strict principles of quantum mechanics or whether black holes stand as exceptions, regions where our current laws of physics fall apart. Whether the answer lies in information being preserved or lost, this riddle opens a gateway to the most profound secrets of the universe, secrets that could someday reshape how we understand space, time, and the structure of existence itself. For now, the paradox stands unresolved, a vivid reminder of the sheer complexity and awe-inspiring mystery woven into the fabric of the cosmos. Ripples through the cosmos. Unveiling gravitational waves. Gravitational waves, tiny distortions rippling through the very structure of space and time, stand among the most compelling and groundbreaking consequences of Einstein's general theory of relativity. For over 100 years, they remained a theoretical concept, seemingly untouchable and out of reach. But in 2015, after many decades of tireless scientific dedication, these unseen waves were detected for the very first time, confirming one of the deepest and most long-standing predictions in modern physics. This discovery launched a transformative era in astrophysics, enabling humanity to hear the cosmos in a completely novel manner. The roots of the idea trace back to Albert Einstein's 1915 publication of general relativity. This revolutionary framework reshaped our entire comprehension of gravity, not as a force acting between bodies, but as the bending and shaping of space-time itself under the influence of matter and energy. To illustrate, picture space-time as an immense flexible sheet. Placing a heavy sphere in the middle causes the surface to deform and curve. Smaller spheres nearby would roll inward along these curves, much like how planets move around stars due to the warping of space-time. Einstein's field equations indicated that when massive objects shift, they should send ripples across this space-time fabric, gravitational waves. These ripples are typically generated by the dramatic acceleration of colossal objects, especially in cosmic events like the spiraling collision of black holes or neutron stars. Still, even Einstein was uncertain whether these waves could ever be captured. Their effects by the time they reached Earth would be so minuscule, they would seem practically impossible to detect. The notion of detecting gravitational waves was mesmerizing, yet it posed an enormous challenge. These disturbances would alternately stretch and compress the dimensions of space, but the resulting changes in length would be unimaginably tiny, even less than a fraction of the width of a proton, rendering conventional instruments ineffective. Even in the event of two black holes colliding, the impact on physical distances would be nearly imperceptible. That's where LIGO, short for the Laser Interferometer Gravitational Wave Observatory, came into the picture. This groundbreaking venture was the result of decades of research and collaboration by scientists like Rainer Weiss, Kip Thorne, and Barry Barish. Initiated in the 1990s, LIGO's mission was to capture the faintest shifts in spacetime by precisely measuring the distance between two mirrors located miles apart. LIGO employs a powerful instrument known as an interferometer, which works by dividing a laser beam into two paths sent down long perpendicular tunnels. Each beam bounces off a mirror and returns to recombine. If a gravitational wave passes by, it subtly changes the length of one arm of the detector, producing a minute interference pattern when the beams merge again. This tiny variation, although incredibly small, can be identified with highly advanced detectors. The signal, lasting less than a single second, produced a unique chirp, a swift increase in both frequency and strength as the black hole spiraled inward and coalesced. The collision was so violent that it unleashed more energy in a fleeting moment than all the stars in the observable universe emit combined. This tremendous burst of energy was carried across the cosmos in the form of gravitational waves, ultimately detected by LIGO. This groundbreaking detection was a pivotal achievement in physics and astronomy. It confirmed Einstein's century-old prediction and unveiled a completely new method of observing the universe. The discovery, made possible by the combined efforts of scientists worldwide, was a profound affirmation of decades of ingenuity, perseverance, and faith in an idea many had once deemed too speculative. Gravitational wave detection reshapes our understanding of the cosmos. These waves allow scientists to listen in on immensely violent and high-energy occurrences from regions far beyond the reach of traditional light-based telescopes. They convey data from the most intense environments in the universe, places where space-time twists to extremes and gravity reigns supreme, such as during black hole collisions, neutron star crashes, and explosive supernovae. Before this landmark moment, astronomers relied solely on various forms of electromagnetic radiation, light, radio waves, X-rays, to study the universe. But gravitational waves represent an entirely different kind of signal, offering a peek into hidden corners of the cosmos. They help unravel mysteries surrounding black holes, the genesis of galaxies, and the underlying architecture of spacetime itself. Following the first detection, LIGO has identified numerous other events, including neutron star mergers, crucial for explaining phenomena like gamma-ray bursts and the synthesis of heavy elements such as gold and platinum. The field of gravitational wave astronomy has since flourished, with global collaboration fueling future discoveries. Other detectors like the Virgo Observatory in Europe and the upcoming space-based LISA Laser Interferometer Space Antenna promise to deepen this exploration. The observation of gravitational waves not only reaffirms Einstein's insights, but also invites us to challenge and expand our current understanding. It sparks fresh theories, inspires new lines of inquiry, and empowers scientists to explore places and processes that were previously off-limits. One of the most exciting opportunities is the chance to examine black hole interiors, zones from which no light escapes. Gravitational waves could provide an indirect means of exploring these enigmatic regions. Furthermore, this new observational tool allows researchers to test Einstein's theory in extreme scenarios, where conventional physics may not apply. Think of a tranquil lake. When a rock is tossed into it, waves ripple outward, telling us about the event. Similarly, gravitational waves propagate through spacetime, carrying vital clues about powerful cosmic upheavals. These waves tell the story of black hole fusions and neutron star collisions, the most energetic processes we know. Once regarded as mere theoretical whispers, gravitational waves have now become a vital instrument in cosmic exploration. Their detection marked the beginning of a new chapter in astronomy, one where we can hear the universe speak, revealing mysteries deeper and more intriguing than ever imagined.